Hello everyone, welcome to the next installment from the Comms Guy. My name is James Powell and I work for JCOM Automation up here in Peterborough, Ontario, Canada. And today I'm going to be talking to you about the history of industrial Ethernet. And whenever I approach a technology, I always find it interesting to see where the technology came from, how it was developed, how did we get here from a historical standpoint, and particularly with with the Ethernet protocols. They've been around for a long time, 20 years. Why didn't this happen 20 years ago? Why is it happening now? So let's get started. I'm going to go over the origins of Ethernet, the rise of open protocols, talk about why Ethernet now, talk about the OSI model and the different Ethernet protocols, and then go through an introduction to the three main industrial protocols. Now, the origins of Ethernet, it was first developed back in 1973, so quite a long time ago, by Robert Metcalfe and David Boggs at Xerox at PAX. And Metcalfe eventually joined Digital Equipment Corporation, and it eventually became an IEEE standard. Here on the screen we see the very first Ethernet twisted pair transceivers, and one of the first microvaxes, and the computers used way back then. So the protocol's been around for really a very, very long time. Now, the first applications were in universities, engineering labs, engineering offices. We had the very beginnings of the internet was developed at this time using Ethernet based protocols, and the whole system was very engineering based, and offices, labs. And as we can see here, I'm showing a CAD drawing, and that's actually the first time I used Ethernet in an industrial setting was with a CAD system. I was a Microvax system manager back over 30 years ago, dealing with Ethernet. So I've been working with Ethernet for a very long time. Now, these first environments, and actually the picture here in the upper right hand corner is from GE Peterborough, and which is where I was a VAC system manager 30 years ago. And we can see a terminal station with and having one very, very small screen and a printout. These early days of Ethernet, we had low electromagnetic interference. Everything was office based. The grounding method wasn't defined. It wasn't, basically. But also, missed packets weren't a big deal, because Ethernet 30 years ago was carrier sense multiple access collision detect, CSMACD. Now, what does that mean? What that means, and it's shown here, is that the one device would send out a message, and if it sensed a collision, it would back off a random amount of time and then try transmitting again. So it would send out a message, so it was multiple, and different nodes on the system could each send out a message whenever they wanted, multiple access. Collision detect, it would sense that there was a collision, and then it would retransmit. It worked, but it was very non-deterministic. It was also, at this point, half duplex. Only one person could talk at a time. Now, going forward, so I was involved in VAC system management in the 80s. going into the 90s is really when the first industrial Ethernet started being applied. And in this case, the application was with HMIs, human-machine interfaces, or man-machine interfaces at that time, and talking to PLCs, programmable logic controllers, for programming them over Ethernet, and also for providing human-machine interfaces, so pulling data, and all for monitoring purposes. So now, quite often it was point-to-point or very small networks. The protocols being used over Ethernet were all proprietary. They were owned by a particular company, and it was non-deterministic. But because we were dealing with purely monitoring or programming, the fact that you'd miss an odd packet here and there wasn't a big deal. You know, Ethernet was still fast at that day. It was 10 megabits per second time period, but still, you missed a packet, you're looking at visualizing data. Your update times, you know, once every few seconds was oodles, so you could get the small amount of data back and forth easily within that time period, even if you missed a whole lot of data, a whole lot of packets. So it definitely worked well in this sort of application. Now, when we say industrial Ethernet, we're referring to really a standard Ethernet protocol with rugged connectors, extended temperature switches that's used in an industrial setting. This is a Wikipedia definition, and it points out things that, you know, it must be able to work in harsh environments, temperature extremes, humidity, vibration, excessive vibration, and it also that the use of fiber optics reduces the problems of electrical noise and provides electrical isolation. So Wikipedia also suggested using that. And it also points out industrial use of Ethernet employs full duplex standards and other methods so collisions do not occur. Because collisions for control is a really bad thing. Now, in the early 90s, collisions did occur. It was non-deterministic. We had questions about noise immunity, the ruggedness, the robustness, and there was certainly a lack of open protocols. Basically, the technology was not there, but we were learning. So early 90s, not quite ready. The rise of open protocols also occurred during this time. So in the 90s, we had Ethernet stuck with still being non-deterministic, and industry started to shift towards open protocols. For years, the protocols being used in all the factories were proprietary, both on the Ethernet side and on the serial side. And what this meant was that one company could come in and offer a very good price to a factory or a process plant to go with one particular technology. And then once the plant went for that, their only source for replacement parts for additional I/O racks or replacement I/O racks would be that one company, because they used a proprietary protocol that they only sold. That meant that the company could jack up the price with no effect. Or the company would have no recourse. It would still have to buy from that one company. And this wasn't a very good situation for end users. And there was a push in industry to come up with open protocols, ones that weren't owned by any one company, where multiple vendors could use that protocol. In 1993, PROFIBUS DP was developed and released. It was based on knowledge learned from Profibus FMS, and it was designed to connect field devices to a controller. At the same time, DeviceNet and ControlNet were being developed as well. The big thing with the open protocols, you weren't locked into any one vendor. Lets users get the best in class, and another effect of it was on innovation. You could have third-party companies come in and innovate neat products that, if you're just one vendor producing everything for a plant, you're limited in what you can do. Even the big guys, General Electric, Siemens, there's only really so many things that they could do. So in the case of Profibus here, I show the example of ProfiTrace, diagnostic suite that was absolutely brilliant. It was developed by a third-party company called Procentec, and it was born out of field service. So the field service people would come in and suggest to their R&D department, we really need a tool that can do this. And they developed this fantastic troubleshooting tool. And this innovation wouldn't have happened if it was a proprietary protocol. So there were distinct advantages to having open protocols. So why Ethernet now? What happened? What changed? We developed a series of open protocols based on different serial physical layers. Why get into it now? Well, one of the things is, industry was out developing open serial protocols for themselves. The Ethernet protocols really started to dominate the office and the home environment. And for that matter, actually, it was still being used in industrial settings. So we were gathering information on how it was actually working in industrial settings. The other, I think, big reason that the Ethernet suite of protocols have really dominated the office and home and is now dominating industry are for the following benefits. It's certainly easy to wire. It has versatile topology, fits anywhere. It can use different types of media, wired, wireless, fiber optics. It's very fast, so it moves a lot of data. Simple to use, and it can have great noise immunity as well. So certainly these benefits really spurred on the domination in the office and the home environment. And really the big thing for going into the industrial setting is that we needed determinism. For industrial control, you need to know when a packet's going to arrive, at least within a certain time period. If it's completely random, that just won't do. Long delays, you don't want to hit an e-stop and then sometimes it just takes 10 milliseconds for it to stop or to issue the command to stop. Sometimes it takes 5 seconds. No. We wouldn't want stuff like that. So we really needed determinism. And how we got that was by new switches that utilized full duplex communications and ones that had developed high-speed data storage and forwarding of messages, store and forward. These new switches had electronic technology that, to be fair, we probably couldn't have done 30 years ago. And now we can. So these new smart switches, they're really the center of industrial Ethernet, ones that can eliminate collisions and repeats. And that was really the major development into deterministic network. So over the past, well, close to 20 years, the first Ethernet protocols were, at first all the Ethernet protocols were proprietary. And then as the open protocols started becoming really successful, the different companies who had developed the serial industrial protocols, basically Open Device Net Vendor Association, PROFIBUS International, the Modbus Association organization, they decided, okay, we need to develop an Ethernet-based protocol. Modbus was actually the first one to do so. And they used their experience with Modbus RTU to design Modbus TCP. It's a relatively simple protocol, does the job, and we'll talk about it more later. ODVA, Open Device Net Vendor Association, used their experience with ControlNet and DeviceNet to design Ethernet IP. And PI, Profibus, Profinet International, used their Profibus experience to design Profinet. So when we say Ethernet, what do we mean? Well, Ethernet itself is really just talking about the cable, be it coaxial, fiber, or twisted pair. You have an Ethernet driver that sends ones and zeros out over the wire to another Ethernet driver receiver. There is sync data, header, data, and a trailer. And it's just talking about how to get ones and zeros from point A to point B. That's Ethernet. Now, when we say protocol, the Webster definition of a protocol is a set of conventions governing the treatment and especially the formatting of data in an electronic communication system, as in network protocols. And a set of conventions or a set of rules is really what we're dealing with here. So when we say Ethernet, we're not really just talking about the wire, we're talking about the whole suite of different sets of rules, different protocols. And there's been many protocols developed over the past 30 years for the office environment and for the home environment. Many of the words on the screen you're going to be familiar with, or you may not know the meaning of them, but HTTP, you've seen that on your web browser, FTP, Telnet, you probably have heard of. Certainly we've been talking about Ethernet IP and Modbus, and TCP, UDP, all these different acronyms will be should be familiar to you. And these all make up the alphabet soup that is Ethernet, a collection of many protocols. So there's a lot of different protocols. Some do the same thing. And they're actually designed so that you can remove one, plop in another. And how it does this is by following another convention called an OSI 7-layer model. Open System Interconnect model helps you conceptualize communication functions. And what it does is breaks the process of communicating from point A to point B into 7 different layers. And the idea is that if you program each of these different layers separately, you can sort of mix and match and plug in. Doesn't quite work that way. And sometimes we find that different protocols will be combining different layers They may combine two layers. And so some you can whip out and plug into something else, some you can't. But for the variations that exist out there, actually works remarkably well. So let's just quickly go through these layers. There's to do justice to this model would actually be an entire presentation on its own. But just a brief introduction. Level 1 is the physical layer. It looks after getting the ones and zeros from point A to point B. The data link layer looks after the grouping and ungrouping the data into packets. It also handles flow control, frame synchronization. The network layer provides routing and forwarding information. Transport layer ensures complete data transfer. Session establishes, maintains, terminates connections between application. Presentation layer transforms data into the required format. Encryption are just different formats. And the application layer supports the end user processes. The actual flow of information goes from the application layer on device 1, and the packet is built up through each of the different layers. More data is added until it gets finally down to the physical layer, where it's transmitted over to the second device and then decoded as it goes up through the layers. Now, the three main industrial protocols, and I say three main because this is accounting for 80% plus of the industrial networks out on the marketplace right now. Profinet and Ethernet IP, depending on which study you see, are either neck and neck or one's leading the other. And Modbus TCP isn't up to the same level as Ethernet IP and Profinet, but is still a significant contributor. So these three are really your three main protocols. They've approached how to do it quite differently. Modbus rides on top of the standard Ethernet stack, and it's shown here on the left. We have Modbus going through the TCP stack, which is really the main transport protocol used for the internet, and so it really rides on standard Ethernet, standard internet Ethernet really, and because it rides on top of that, there's a bit of a price to be paid. The TCP stack is very slow, can take upwards to a second to process things. And there's a fair bit of variance in the timing as well. It's very secure, but it takes a fair bit of time. So with Modbus going that way, they were able to quickly port Modbus onto Ethernet. So that was a plus. Made it pretty easy to use. That was a plus. It's pretty easy to understand. That's a plus. Really slow. Not so much of a plus, more of a negative. Ethernet IP said, well, TCP is still a great way of establishing communications, but for actual control data, we need something much faster. UDP is much faster. So it sets up all the communications using TCP, slow, which is fine, and then for actual data exchange goes onto the UTP high-speed communications. Profinet approached things quite a bit different. It said, well, to set up communications, we're going to use UDP because we still want to set things up fast, but for actual control data, we're going to use our own stack called real time. And because we're essentially bypassing a lot of the standard stack, we make the sucker fast. And so as a result, Profinet is much faster and with less dither than Ethernet IP. To really discuss the details, the differences between these three protocols, actually it takes me a better part of 2 days to do it proper, so this is a rather quick summary. Modbus TCP is very simple to use. It works great over the internet or a wide area network, and it's great for monitoring. But because it uses just the TCP stack, I'm really not big on using Modbus for control. Like if you have a really slow process, yeah, you can get away with it. Particularly if you isolate the network without any other TCP network traffic going on. But otherwise, you really need to use either Ethernet IP or Profinet. They're both far more complex than Profibus TCP. They have more processes going on, but they are both great for control applications. So, to summarize, Ethernet is really not, or was not, suitable for industrial communications at first. That collision sensing, multiple access, you couldn't use that for control. So they needed development of modern switches for deterministic communications. They needed development of open industrial protocols, because nobody wants to be locked in to a proprietary protocol. And as we see in my Ethernet classes I teach, the development of shielded cabling was pretty important. But now, basically, we have everything. It's ready to go. The modern protocols have been developed. The intelligent switches have been developed. The shielding has all been well defined. The installation methods have been defined. We're ready to go on this technology. Now, to learn more, JCOM Automation Incorporated has a 2-day Industrial Ethernet Essentials course. You can get more information up on my website, www.jcomautomation.ca/training. This is a great 2-day course where I teach what do you need to do or know to do an industrial Ethernet application. What is Modbus TCP? What is Ethernet IP? What is Profinet? I have a lot of labs, and I have labs that compare the three protocols in a great environment. I'm using some software by a European company called CODIS, and it's fairly easy control software to use. The big thing for me is that the CODIS supports Modbus TCP, Ethernet IP, and Profinet all in the same controller. And the controller happens to be a Raspberry Pi, which is sort of cool in itself. So it's fun going through the labs, and you really get to see on how the three protocols work and look, because I also teach about Wireshark as well. To learn more about Profinet and industrial Ethernet, there's a book called Catching the Process Field Bus, an introduction to Profibus and Profinet. It's available as a free download from profinet.com, and the link is shown there. Yes, I'm a little prejudiced about the book since I wrote it along with my co-author, and there's also resources available up on the Profinet website, and I believe ODVA has some additional information as well. So thank you very much for your time and attention today on listening to my YouTube video. I hope you've enjoyed it. If you have, please subscribe, and also give me a like. I'd appreciate both. Take care. Have a good day. Bye.